Welcome back, everyone. It's been a while. I'm really glad to be back with another video to help you improve your skills as a SQL developer. You know, so much of the material out on YouTube is, in my opinion, lifeless and likely AI generated. So I'm committed to producing original content with simple examples to help build your skills. Today we're going to cover the very basics of SQL Server indexing by comparing a table with no index at all to one with a very simple primary key. Future videos will build on this concept, but I really want to get the basics down. So what I want you to start thinking of is, suppose you had a pile laying on the floor of 100 index cards, and all you know is there's a number printed on the index card, and your task is to find the largest number. Without any additional information, all you have to go on is looking at every single card, finding the highest value. You pick up one card, it says 247. You pick up a second card, it says 125. Well, you can discard that. You pick up a third card, it says 476. Well, now that's the highest. Since you don't know anything about the ordering, the lowest value, the highest value, you need to look through every single card. What SQL Server calls this is a heap. It's just a pile of data. It's completely randomized, and essentially the query engine, the computer, the software needs to look through all of the information to find that value. And so let's go through some examples here. Within SQL Server, we'll go ahead and clear out our table. Going to create a table called unique integers. All it has is an identity value and a random value. We're going to generate 10,000 unique integers between minus 500,000 and plus 500,000. All we do here is we select 10,000 sequential numbers, we scale it a little bit, and then we randomize with this order by new ID. So we'll go ahead and run that, ignore that on the bottom. And if we said give me the count, sure enough, I have 10,000. The top 20 ordered by that identifier, so there is an identifier. And you can see the random value. It's all over the map. Small number, 8,700, minus 363,330, positive 259,400. There's 10,000 of these. You can almost look at it as 10,000 index cards, all with a random value. Now, let's say we wanted to find all of those that are greater than 125. I have this value, this icon selected here, which shows us the actual execution plan. And we're going to use that to pull some information out about the query. Go ahead and run it. It found that there are 4,999 of our 10,000 that have a value greater than 125. If you click here, look at the execution plan. Given no other information, it needs to scan the table. This is akin to you looking at every single index card individually. And you see here, the two I want to point out is the actual number of rows read is 10,000, and the actual number of rows for all executions is 4,999. So it ran through all 10,000 rows and found 4,999 that are relevant. So it needed to read the entire table. And it ran quick, less than a second actually. But obviously this is a very simple table. If you had a Y table or hundreds of thousands, millions, billions of rows, it needs to look at every single row. Not necessarily all the time. Here's an example of the top 10 where the random value is greater than 497,000. It found the 10, and it was able to stop after 3,560 rows because it found all 10. If you can imagine, once you find the 10th, you're done. You're not asked to find all of them. Top 10 where the random value is greater than 97,000. In this case, it only took 23 executions before it found all 10. It's just the luck of the draw. Top 10 where the random value is less than minus 499,000. Well, in this case, it only found 9. It turns out there are not 10 rows. And as you can imagine, it needed to search through all 10,000 down here to find the 9 that it was looking for. It was actually looking for 10. It got to the end, it only found 9. A couple of other examples. Let's find the minimum random value where the random value is greater than 142,572. Turns out that is 142,600. Here, it needed to scan 10,000, so it scanned the entire table. Now, what is this 3,575? In this case, it needed to look at the entire table. It picked all of the unique integers greater than 142,572. It turns out to be 3,575 of them. And then this operator is the minimum. And that's how it was able to pull out 142,600. You can see that here. There are 3,575 total out of the 10,000. That's greater than 142,572. So in all of these examples, all 6 of these select statements, you can tell in most cases it needs to just search through the data, either all 10,000 or until it reached a threshold in these 2 cases of the top 10. Recall for this third one, it needed to look through all 10,000 because it never found a 10th. Now, what happens when I add an index? I'm adding a primary key on the random value. Because this is a very simple table, what this does is 2 things. One, it guarantees uniqueness for the random value. And 2, it is going to order the data on disk in the order of the random value. The default is to make this a clustered index. If you've heard of that term before, we'll get into that in a future video. It's really just the order of the data on disk. So we'll go ahead and execute that, and then let's see what happens for our 6 select statements. Same. In this case, it only needed to scan half the table because it knows exactly the order of the table and pulls back to 4,999 for the count. Top 10. It only needed to scan 10 to pull back the 10. Run these 2 together here. In this case, again, the top 10. In this case, the 9, because it knows the order of the data. Because of this index. And you can see here, instead of that table scan, it has this clustered index seek symbol. So the seeking is, it's very targeted. It's able to navigate the structure of the data to pull back exactly what you need. The minimum random value. Here's our clustered index seek. And only needed to read 1 row. It was able to find exactly where to go, able to navigate that structure. And so even in this very simple example, you can see that if you tell SQL Server about the order of the data, if you tell it to store the data in a certain way, you can go from 10,000 scans down to 1 scan. even for a very simple 2-column wide 10,000 row table. But imagine if this was 500 columns wide and a couple of billion rows, how many operations you're saving and how much more efficient your queries are. Going forward, we'll have some other videos where we're going to dive much more deeply into indexing. I mentioned clustered indexing. There's a concept of a non-clustered index, a covering index. There are included columns in an index as well. We're going to hit all of that in future videos. In this example, I really just wanted to show the difference between a completely unindexed table, and think of that heap, think of that pile of data, and how you have to search through all of the different cards to find your information, versus just a very simple, I want to order it by random value, and how much more efficient that could be. Think about if you got a deck of cards labeled 1 through 10,000, and you needed to find the minimum value, the maximum value, etc. You can be much more efficient, and SQL Server is no different. Thank you for watching. If you got something out of this, please feel free to consider subscribing and be notified when the next video comes out. And I'll see you in the next one. Thank you.